in these public hyperscalers? Is there something that has to be done, or we can just use them as they are?
Other misconception is probably about what is quantum parallelism, and it's about this like how can they be in the same state? Quantum computer or the hardware for it is ready. They might be able to decrypt it. It's easy to panic then of like really to protect everything, but think of like what data is in there. That's maybe my advice, right?
Welcome to Blackbox Debugged. I'm Dzefris, your host, and today's topic that we'll be debugging is quantum computing and cybersecurity. Our guest today is Armin Berberovic. He's a security architect. Hi, Armin.
Hi, Dzefris. I'm happy to be here.
Can you tell us something about yourself?
Yes. So I'm Armin. As already mentioned, I'm security architect in the cloud security services. Outside of corporate life, I'm also an author. So I like to write articles. I'm blogging at cloudsec42.com. Some of our German readers might have seen my articles at heise.de and the IX magazine. So that's what I like to do in my free time. And I'm also a Microsoft MVP.
So that's pretty cool. This Microsoft MVP, is it like most valuable player? Sounds like a basketball title or like sports title.
Close. It's the most valuable professional.
Mm-hmm.
So let me maybe say something about it, okay? It's like a community award that Microsoft gives out to, people that contribute to the community. So I do that mostly through my articles that I write, through my blog posts. I do sometimes speaking engagements, or I have a GitHub repository where I put code in. So there are many ways you can contribute. As I mentioned, you can speak, you can write, you can do community work, answer questions in boards on the internet. And that's basically it. So they honor you for your community contributions, and it has some peaks to it.
Mm-hmm. Interesting. And is it related to cloud solutions for Microsoft, like Azure, or is it in general?
Oh, there are a lot of categories for Microsoft MVPs. So I'm right now an MVP for cloud security.
Mm-hmm.
You can become an MVP in, I think, basically everything Microsoft offers. Don't cite me with that, but there are a lot of variants of that. The M365, MVPs, Copilot.
Mm-hmm. Mm-hmm.
Yeah, so it's pretty much covered.
Okay, interesting. And you mentioned your cloud cybersecurity MVP. So
exactly.
The most valuable professional. Today we have a lot of hyperscalers, a lot of cloud solutions there, cloud platforms that can be used, including the Google, so GCP, the AWS from Amazon, the Azure from Microsoft. They're quite used across the board around the world. Would you tell us a bit more about the cloud security in these public hyperscalers? Is there something that has to be done, or we can just use them as they are?
And there's a lot of things to do. So many people think that you go to the cloud and then a Microsoft or Google or whoever's cloud you choose takes everything from you. That's not the case. So you have a shared responsibility. You're of course responsible for some things. Most things that happen on site are taken over, but for security you are definitively responsible. And there's plenty of stuff to do there. I think one important topic we should talk about is isolation in the cloud. So if it's not obvious why we need isolation, okay, you don't want to have an incident and have your whole cloud owned, all of your environments, right?
Mm-hmm.
So you isolate them. So in order that in case there's a breach, in case there's a vulnerability, the impact's not as big as it right? That makes sense.
Yeah, that definitely makes sense, right? I mean, obviously, security is in software industry overall not always the number one priority, even though it should be. And I mean, in certain domains and industries like aviation industries, it's taken quite seriously. But there are different ways how we can do things, right? In respect to security, also in cloud. How does GitHub's concept fit into the picture?
That's a good question. Okay. Like, so there are different ways you can use the cloud. Of course, like the cloud providers provide a lot of like portals where you can go like portal.azure.com and just like click everything together. Okay, but this is not so much the favorite way anymore. Rather, you want to use what you mentioned, GitOps. And there are like good reasons for doing GitOps. Okay, you can like version your infrastructure. You have like review process in it. Like, you know, you do something in GitHub, you do a PR, it has to be reviewed. So basically, you take the peaks from software development and you bring it also in the cloud. You can also easily redeploy it in case, like, you know, you want to spin up a new environment, you have it already in code. Everything's really simple with that. Okay, so these are the peaks of GitOps, but GitOps puts us, like me, as a security architect, into gives me new challenges. Let's put it like that. Okay, like doing isolation in the cloud, it's quite simple. You in Azure, you would use management groups. In GCP, you would use folders or projects, depending on how you want to scope it. But with GitOps, you have a whole new dimension where you have to bring the isolation as well to it. Okay, and that's what many companies do, because I think they just want to get started with GitOps. They have like one service account with God mode powers. That you don't want, because now we're back to the first thing that I mentioned. Okay, this repo gets owned, you are owned. So we don't want to have that. So we should also think about how to bring isolation to GitOps, and in this case, like GitHub and the pipelines, you know.
Yeah, so it's like always like the weakest link is the one that can break the whole chain.
Exactly.
In this case.
So you're only as secure as your weakest link.
Yeah, exactly. What would you recommend? Like, what are like the best practices here that should be followed in this area?
So there are multiple approaches to that. Okay, like you can take different routes, but one thing I would at least recommend is like to have one service account per environment and with a pipeline. Okay, so how you could solve that is basically having one GitHub repository, and like this comes with a GitHub action, you know, does the pipeline steps and an identity behind it. My first recommendation would be like do a one-to-one mapping between a pipeline and between like, let's say, a management group in your environment. All right, this may be the most basic one. Of course, if you can use with, like workload identity federation, don't rely on secrets. Okay, the less secrets you have, the less headaches you have, the less things could leak. And the other topics, they're a bit more advanced, but maybe for people that are already using that, I also have a third recommendation, and this is be careful with like, how to say, let's call it open identifiers. Okay, like usually you would have YAML files in this repository. And if you can like just specify the name of a service account, no, not of a service, but of a storage account, things can go pretty bad. And fixing them is also quite difficult. So if you can kind of try to avoid that user input is just a freely usable identifier, like the name of a storage account, the name of a VM or whatever. Expanding that takes maybe this thing a bit too far. But it's on my blog. I've explained it. I also have an article about it.
Yeah, sure. So our listeners can also read the post on our blog as well.
It's a bit difficult without images to explain that.
Of course. But in short, they should also keep, I think, their secrets in a secure place, right? Like if they have secrets, they shouldn't have them in the code.
If you have secrets, don't commit them in your repository.
Great. Right? That's a simple one. I think that can be followed without pictures.
Yeah.
Awesome. So we talk now about cloud, and of course it's a very, very popular topic for quite a few past years, or maybe more than a decade now. There is another topic that is coming and going out of the picture depending on like the news outlets and like the new discoveries and things like that. And that's quantum computing or quantum computers.
Exactly.
Can you tell us in short what a quantum computer is, and is it possible that quantum computers will replace the regular computers, and are all the quantum computers same?
Oh, that's like a lot of questions. So let's start with maybe the most often asked question. No, quantum computers won't replace classical computers. Okay, this I think everybody is clear on that. There's no reason to do that.
Mm-hmm.
And you might think that this is probably a way because of some misconceptions about quantum computers that we will also talk about, like quantum parallelism. Okay. But in general, no, they won't replace it. Think of a quantum computer more like a GPU. Okay, like next to your CPU and your GPU, you would be able to use a QPU, so a quantum processing unit, to solve very specific tasks.
Interesting. So, and how are then these quantum computers different between each other?
Yeah. Okay, so that's another thing. So, like quantum computers, they're often discussed like as a single thing. Right, and we are kind of used to that from classical computers. Classical computer is made of transistors. I think everybody agrees on that. That the technology that nobody would go and build water pipes and tell you this is my new computer.
Yeah,
very elaborated technology, like a lot of development behind it, but it's standard now. For quantum computers, we don't really know what's the standard way to build a quantum computer. Okay,
we have not standardized it yet, right? They're all like. IBM has one, Google has one, other companies have the other approaches, and then it's not there is no industry standard yet to how to make them.
Yeah, so there's no industry standard. There are like different approaches that different manufacturers like follow. I think the three most common ones that you will see for a gate-based quantum computer. Okay, there are also different kinds of quantum computers. Usually we talk about gate-based quantum computing. And the three most used technologies are like ion-trapped quantum computers, neutral atom quantum computers, and like superconducting circuits. So this is also, when you research it, that's usually terms you stumble upon.
Yeah.
And maybe I should explain a little bit.
You can definitely, yeah. That will help me also understand better.
Okay, that's maybe so. The main difference between these technologies is like, do you actually use an atom for the computation? Then you would use an ion trap or a neutral atom computer. Or do you try to replicate the properties of an atom? And this is like with superconducting circuits, that's what they do. And so they come with advantages and disadvantages. And this is probably a good start to like debunk already maybe one misconception. It's not about the amount of qubits. Okay, I can already tell you, like, each technology can support different amount of qubits. This is like how the case is right now, but it's not only about that. How do I start? So like what are other factors that are relevant for a quantum computer other than qubits? And you have to think about like qubit connectivity. Okay. Like qubit connectivity means from a physical point of view, and I'm not a physician, so it's more like it has impact on your algorithms, but I cannot explain you in total detail what this means. But it's like, how are they wired together? Okay, like if you have a gate and you want to run it on a single qubit, can you run, or like you have a 2-qubit gate, can you connect any qubit with any qubit? Okay, this is like full connectivity of the qubits. So like ion trap quantum computers, they come with that. But on the then they come with like not so many qubits, like 100 qubits around that. The other thing are superconducting circuits. And I'm really generalizing now. There's a lot of movement on that. But in general, you don't have that amount of connectivity with them. Because you can reach like nearest neighbor connectivity. So you can only connect like one qubit with its neighbor. And this, also when you write an algorithm, this puts you like, this is effect to your algorithm. You can work with swap gates for like change them, but in general, connectivity is another important thing.
Yeah, I mean, there is this like, I think another thing that about which everyone thinks about when they hear quantum computing, and that's about like 0, 1, and 1 and 0 being 0 and 1 at the same time, and being. So can you explain us that a little bit, and what is quantum parallelism? Yeah,
that's actually a good one. So the other misconception is probably about what is quantum parallelism, and it's about this like how can they be in the same state? Okay, So maybe the main difference between classical parallelization and quantum parallelization is that at the end of a classical parallelization, you know the results, right? You do not only calculate it, we can read them out.
You get 0, 1, 1, 0, 0, 0.
Let's make a simple example, okay? Let's say you have an algorithm, and we can simplify it by just say you have a function, or you have a simple gate, like a NOT gate or something. And you have an input and you have an output. And what your algorithm does is like take the input, run that gate on it, and create the output. So you map input to output. Very simple. So on a classical sequential computer, you have two inputs. Let's say you have two inputs. You take the first input, okay, at T1, you calculate the f of x of it, and at T1, you read it out. And then you repeat and read at T2 the second value. Mm-hmm. And then you know the mapping. You know your x1 and x2, and you know the f of x1 and f of x2, right?
Mm-hmm.
After T2.
Sounds definitely more complicated than sequential computers. So.
Okay. So maybe I'm not doing a good job.
No, you are. It's just that I think the whole paradigm is completely different. Like if you're coming from like what we call traditional like CPUs or like the processors that are processing the one value in their state at the time. Let's call it like that. And if you go to quantum parallelism, then quantum computing, the thing gets quite fast, complicated, very fast, right?
Very fast, complicated. Okay. Let me try to give a summary of that. So on the classical parallel computer, you would know all the values you calculated, right? On the quantum computer, at the point where you measure, you basically destroy the superposition. And the superposition is what people describe as being one or two at the same time. So I think a better way to put it, it's at the same time, it's both values. But if you really work with algorithms, the thing that you care about are the things that you can read out. It's better to say you have a certain probability to measure either 1 or 0. And your quantum algorithms, they try to influence that, okay? Mm-hmm. So that's the thing. So like in quantum parallelism, you put it in a superposition, you run your gate on it, whatever it is, and at the end, the results are probably somewhere, but you have no chance to measure them. You will always get one value, let's say at random, if it's an equal superposition.
It's really fascinating. It's amazing, like the whole field of quantum computing, and I find it really interesting, and it's really interesting just to think about of how they can impact our lives in the future once they're like adapted on a larger scale, or hopefully one day we have them running in our laptops, phones, or something like that, if it will be ever possible, right? I mean, we had transistors in the past, right, that were basically as big as this whole studio that we are sitting in, or even larger, like the whole building. And now we have millions of them in our devices, which are like smaller than our palm. So
that's true.
But they're not only like the benefits or like the positive side, like with every technology. There are also some worries that people are worrying about cybersecurity and the impact the quantum computers or the negative impact they could have on the encryption. So are we lost there? Will all of our accounts be hacked and there is no need for passwords anymore? Or can quantum computers help us with encryption as well and not only destroy it?
That's also what you're referring to is, let's start with this, how they break encryption. So that's Shor's algorithm. So encryption is based of calculating prime factors, okay? And Shor found a really clever way to do this calculation on the quantum computer. So that's why everybody's panicking. And for good reason, okay? Like if we could do this efficiently, like prime factors, calculating prime factors, we would be in big trouble because a lot of encryption wouldn't be secure anymore. The question whenever this comes, when this is ready, it's a forecast. You can never know. 10 years, 50 years, who knows? But in general, and that's one thing that's probably not so obvious, quantum computers, they cannot only break encryption, they can also help encryption. And you remember how I previously talked about the superposition that gives you at random a measurement? You can leverage that.
Of course, then you can actually have better randomness than what we have right now. Something like that, right?
Yeah, so like let's put it simply, so a regular computer is kind of deterministic, right?
Exactly. So it's random, but it's not really random, right?
You have like the amount of entropy in it. Okay, so there are special sources of entropy in it. But let's say they're more or less limited. I mean, people worked a lot on it. Their work usually you don't recognize. And they could lack ever entropy. But the quantum computer, by the fundamental principles, by what the quantum computer works, he has an infinite source of entropy. And you need entropy to generate real random numbers. And real random numbers are the things that drive encryption, right?
Yeah.
So yeah, that's basically the trick. So the thing that I explained before, this collapse of the superposition, it has disadvantages. Unfortunately, we cannot parallelize everything due to that, but it also has advantages. So you can use it in encryption to generate real random numbers. And there are also like dedicated number generators that leverage this quantum effects already. So in commercial products, it's not on a quantum computer, but they leverage the same principles.
And what do you think, is the software industry ready for something like that to happen? I mean, from cybersecurity perspective, I know, for example, that in crypto industry, they're working on specifically on Bitcoin, they're already working on like preparing themselves for the case where you have quantum computers that could potentially affect the encryption, which is very essential, for example, in crypto industry, because it's encrypted, right? So it's very essential. But there are other industries as well where security is important overall everywhere. But in some cases, like in finance or in some critical industries like aviation, others, it's extra important. So do you see that the industry is preparing for that moment? Or do you think it could be doing more, the software industry itself?
So I think people are thinking about it, and the thing about how to address that. And it's a reasonable concern. I mean, a common threat that I hear is like, store now, decrypt later, right? So what do you do about somebody now catching your encrypted traffic? Or he cannot do anything without it. It's encrypted. But he's catching it and collecting it. And at some point, when quantum computer or the hardware for it is ready, they might be able to decrypt it. It's easy to panic then, of like, really, and to protect everything. But think of like what data is in there. That's maybe my advice, right? So how relevant is the data like 10 years?
Yeah, so you mean not everything? You mean not everything will be at risk, or not will be valuable enough to be decrypted, or
like the attacker wouldn't know what you decrypt, right? Probably he's just collecting like traffic as much as he can. But for you as a company, you can think of like, what do you have to protect? What is the data that's still relevant, right? I mean, maybe something is confidential now, but in 3 years, it's already announced and it's not confidential anymore. So like they can freely decrypt it.
Yeah, you mean so the data that we already have and that could be the potential in the future decrypted once we have. So
exactly, that's the attack there.
How about the data that will be going live in the future? So that's something that is encrypted in 10 years, and then when maybe in 10 years we have quantum computers, so that they could decrypt that very relevant data.
So in that case, you should better look into algorithms, that are like already, how to say, resistant against this kind of attacks. So not every encryption is based off prime numbers, and there are alternatives to it. You should probably look into that. Okay, and think about like switch your applications to that, or basically stay on the crypto agile. Okay, be able to switch out encryption, and that's if you're really concerned about it, make your applications at least like crypto agile. That in the future, when things are going downhill, you can just switch out the algorithm you use for encryption.
Interesting. Yeah. So we have to design systems such a way not that just we can change the architecture and the parts of the system, but also specifically the thing that keeps the system safe. So the encryption would be so can you say isolated on the side so it can be swapped, like basically. So it's because in some cases some systems are designed in such a way where it's not so easy to change the encryption that is being used, right? So is this what you mean when you say like keep the encryption agile, that you can easier exchange it in the system?
Exactly, yeah. But you can just switch from one way to encrypt your data to another way without having like disruptions of your applications, of your services, right?
Yeah, totally makes sense. I mean, it's also like the basic software engineering principles, right? So you can
right.
change your system easier over time.
Exactly.
When we are talking about change, there is another thing next to cloud and quantum computing that we've been quite in the media or also hot in the industry for some time. There is AI that was also coming and going, similar to quantum computing, but there is one part of AI which is Gen AI or LLMs, or large language models, that is sticking with us for now a couple of last years. What do you see there? What are the risks in cybersecurity in relation to LLMs?
LLMs can be attacked in two ways. Okay, right. You can attack them as you can attack any application by attacking its infrastructure, and you need special hardening for that. You know, like because you use like probably Azure's OpenAI, you need to know how to make it secure, make it safe. So you can take recommendations that you would anyway give for classical applications, like for example in Azure, use managed entities. And then you don't have to worry about secrets. And as I said before, no secrets, no worries. Okay, like less secrets, less headaches. That's like one thing. The other thing is like attacks to the LLM. Because you can not only attack the application, you can also attack the LLM. And I think one very prominent is prompt injection. People have heard it so far. Yeah, there are two kinds of prompt injections, like either direct or indirect prompt injections. I think the most scary ones are actually indirect prompt injection.
What are the indirect prompt injections?
Let me start with a little bit the step back. Okay, so like you have large language models, they're usually chatbots. And you can provide them data, right? Like have a RAG architecture. So you can provide them your own documents, like an email, whatever, tell him summarize it, please. And he will take that, process it, and give you the summary. So an indirect prompt injection is attacking this data that you submit to it. Okay, like think of an email. Think of somebody writes you an email and you let it automatically summarize by a large language model. The thing is, you can hide instructions in this data. They don't have to be readable for humans. They could be white color on white background. But if you do it smartly enough, okay, during RAG it will be picked up, and the LLM will kind of get this as an instruction. And we have the issue like with LLMs, you have like a continuous stream of tokens. Okay, so they cannot really differentiate between what is a valid instruction and what is like user submitted data. So you're at worries that it will pick up this instruction. Okay, and then from there on, a lot of bad things can happen. Okay, if it supports like tools, if it can call external APIs, and you could even use that to trigger an external API. So it then really depends on what are the capabilities of that LLM. But the sneaky thing is that the user that's using the LLM is at the same time the victim. He doesn't know about it. He just tries to summarize something and get more productivity. And he can easily fall for that.
Yeah, so there are a lot of benefits or positive things that we can also get from LLMs, but there are a lot of risks, and especially in cybersecurity areas, as you mentioned. So the message is be careful what you are putting into the LLM, so into the chat as a user, right? And then also, if you're designing a system, be aware that, I mean, the same things that we have in the past with SQL injections, right, through the input fields in the UI. similar or basically the same good best practices apply in that case as well, right? Like, of course, we have to adopt them. It's not all the same, but best engineering or best security practices apply there.
Exactly, like input validation. Okay, like it takes a bit of different form in an LLM, how input validation works. But in general, you should do input validation. Okay, you can basically use LLMs also to protect against that by trying to identify these prompt injections. They can sometimes take obvious forms. Some days they can be less obvious. So people are already working on defending against that. And as you said, like it's kind of taking best practices you already know and think of it. How do they look for large language models?
Yeah, great. For the end, I have one somewhat of personal question. Should I be worried about my passwords and accounts because of like quantum computing? I mean, you bit already mentioned about that, but let's say of the services that I'm using, the cloud services, like the social media and so on, or like the LLMs, can they somehow attack? Can LLMs be used also in that area to attack my accounts? And should I stop using 1Password for all of my accounts, or the 1Password? I mean, I'm not personally using 1Password, but I know a lot of people are. So maybe you can send them a message.
So please don't use a single password for all of your accounts. Okay. Also, like, don't use corporate and private passwords. Don't reuse passwords in general, but especially not corporate and private passwords. Right? I think that's something everybody would agree on.
Yeah, definitely. And basically, also as regular users, we have to count on the companies that are providing this, that they'll keep our account safe from like quantum computing attacks or something like that, right?
Yeah.
So I can expect that tomorrow my account will still not be hacked by quantum computer.
No, tomorrow, no. Don't worry about our future. All right.
All right. Okay, so for some time we are safe. But we are working as an industry on it, right?
Exactly.
All right, Armin. Thank you very much for joining our podcast and for debugging together with us the quantum computing and cybersecurity. We're looking forward to having you in the future. It was my pleasure.
It was my pleasure too. Happy to be here.